Okay. Today, let's start with lecture 6, product is exponential and the kinematics of open chain. I think I did some modification on this lecture note. I hope you get a new one. I will start over again. So kinematics, last time I was in a rush. Kinematics is, let's first define. I think everyone should have its own definition about what robot means. I want everyone to think about a robot as a, let's say, multiple rigid bodies mathematically. Think about robot mathematically, okay? You may have different type of robots. They may have different look, but mathematically, they are all about multiple rigid bodies, okay? Interconnected, interconnected through joins. Okay, at least the robot we consider in this class is about this kind of robot, multiple rigid bodies, and they are interconnected through joints. So forward kinematics is really about if you have some part of the robot you're interested in, you want to know its pose or configuration in space. For example, if I have a robot, let's say this is a UR3 maybe. This robot, I may be interested in this kind of anti-factor frame, maybe called B frame. So I want to know the configuration or pose. Okay, in the future, I'm going to change interchangeably using these two terms. Pose or configuration, they both include both the rotation matrix, also the displacement vector P. Okay. We're interested in knowing the configuration or pose of B in the space as a function of the joint variables, theta 1, theta 2, all the way to theta n. Suppose we have n joints. Okay. So that's the forward kinematics. And the velocity kinematics really concerns with the velocity of this anti-factor frame or any frame of your interest B as a function of the joint velocity theta dot. Okay, that will be the next lecture. Okay. So today, let's directly jump into the example. Suppose I have this example. I modified the example a little bit, so it's become simpler, so we can truly follow every single step. Suppose I have a anti-factor frame. Let's call that B here. Suppose this is my ZB hat. This is my XB hat. This is my YB hat. I chose this frame arbitrarily because I think this is our interest. Okay. So we call this frame. Let me use that. I call this frame my B frame. Okay, and there's a global frame or word frame. This is my, let's call that frame 0 or frame S. In this lecture, they are the same. They are fixed frame or word frame or inertial frame or 0 frame. It's just one frame fixed in the space. So our goal is actually try to compute the configuration or pose of frame B, which is the T of B, right? That's a homogeneous transformation matrix representing the pose of frame B. As you can imagine that this frame B, T of B, depends on the joint variables. If I have my joint at different position, this frame, its configuration or pose in this 0 space or S frame, it's different. Okay, so it's really a function of theta 1 and theta 2. Okay, so now the goal is just for our goal today is just derive formulas for this kind of pose as a function of theta 1 and theta 2. Okay, so since this guy is a function of theta 1, theta 2, let's first consider the very baby step. Okay, the first step. Let's assume at the 0 position. Okay, both theta1 and theta2, we know its value, and their value is 0. Some kind of standard or home configuration. Let's first find out this. This become a pure kind of a calculation problem. In this case, let's assume our joint, let's do that. Let's assume the home position is this kind of position. Suppose this now is theta2, but when theta2 is 0, it's really kind of aligned. These two arms are aligned with each other, so that will be here. Okay, I'm going to ask you guys, maybe that phone. This position, this current position is the theta1 equal to 0. Here is theta2 equal to 0. I'm going to ask you what this the configuration of B relative to S when this both theta equal to 0.
That's the position is
the position is this point, right? Sorry, the center of the frame will be here, right? If this will be meant to be, if that's 0, right?
Yeah.
So
L1 plus L2.
Okay. Let's say this is my R matrix. That's 0, 0, 0. This is 1, right? The first x coordinate is L1 plus L2.
And the y coordinate is 0, and z is.
Let's call that L0. Okay, that's the link ones.
Z is L0.
L0. Okay. Let's ignore the thickness of those boxes. Okay, so let's assume they are all at the same level. For simplicity. Okay, that's for P. Good.
And orientation.
Orientation, yeah. What's the orientation?
Orientation should be the same as the space frame. So it's the identity.
Okay, great. Right. So that's my. So we want to find. Oh, you can mute yourself now. Okay. All right. That's when theta1 and theta2 are both 0. We have computed the pose. Right. But now we want to find the function. So this configuration or pose will change as we move or increase or decrease theta1 and theta2. So let's do it one by one. All right. Let's fix theta1 at 0. We don't change it. Okay. Now let's think about it. Let's suppose this arm is fixed at the theta equal to 1 equal to 0, and this arm rotate. This is what clockwise, right? Or sorry, counterclockwise by theta2. Then it will have a new kind of configuration or pose, right? So we rotate, let's say about join 2 by theta2. Then we will have a new kind of pose with TBS 0 and theta2. So I'm going to ask you, how do we find this new pose? Okay, I'm going to kind of remind you of a few things before I ask you the final answer. First one is that the whole thing, think about this, rotate the frame, this body 2 or link 2, this is my link 2. Rotate link 2, and as well, you will rotate this B frame as well, right? So rotate B about this joint by theta2 degree. This is a rigid body motion. This induces a rigid body motion for link 2. Okay, and of course for B as well, because B is rigidly attached to link 2, so they're the same. Okay, and I would say this rigid body motion is defined or can be represented, I would say represented by screw motion. This is a trivial screw motion, which only involves rotation, right? So in coordinate free, whenever possible, I ask you to think about things in coordinate free way. In coordinate free way of thinking, let's say, this guy, the TB, okay, and initially will be M, right? Initially we are here. So at the beginning, we are here. M means θ1 equal to 0, θ2 equal to 0, right? Now we apply a screw motion. Let's say this screw motion is called P. Let's call it T hat, all right? T hat, make sure that's an operator, okay? This is a motion, it's an action, it's a verb, okay? Rotate about this by θ2 degree, then you get to where? So this is the reason about the operator, right? So then it will become T hat times this M, right? And this guy, I'm gonna ask maybe Fuzhen, what do you think this representation is?
This is action.
Yes. What's the formula to represent this action?
Formula.
Operator view of homogeneous transformation matrix. So all the matrix can be viewed as a screw motion, right? And in this case, the E to the S2 θ2. Suppose S2 is the screw axis corresponding to this guy, right? This is my joint. This is the S1. So rotation about this axis in space is a special kind of simple actually screw axis. And rotate about this screw axis by θ2 degree is a correspond to a rigid body operator, which is defined by E to the S2 square θ2. So is this okay now?
Yes.
Okay. So in this way, we will have that means this guy equal to E to the S2 θ2 times M. Okay. So this is in coordinate free. I didn't say which coordinate we represent the whole operation. So let's say now let's say we in S or let's say O frame or 0 frame. What we have will be TB in S. Now θ1 is 0, θ2 is θ2 now is equal to exponential of this S2, right? S2 θ2 S2 in 0, right? S2 in 0, let's call that 0 or S. I use 0 or S interchangeably here. And because I don't want to have S of S, okay, so S of 0. And this TB times 0, 0, which is M. Okay, that's our formula for now. But the one thing I want to tell you is that let's use this color. So S hat to 0, not hat, sorry, S to the screw axis of the second joint in the 0 in the inertial frame is actually a function of θ1. Okay, so think about this. So where this S2, this axis is a physical vector, okay, screw axis, and its coordinate with respect to the O frame actually depends on this joint variable θ1. If θ1 is rotated here, then S2 will be rotated as well. Okay, I hope that's clear. So it's a function of θ1. So more precisely, we will write like more precisely. So S2 theta, S2 in 0 is actually a function of θ1. Okay, I should write like this. If we don't write like this, means somehow it's clear from context. Okay, since we fixed, right? We since let's not since, all right. So this bullet point now, theta 1 is 0, right? In this case, theta 1 is 0. So this guy has a numerical value now, right? So let's define, in this special case, let's define the S2 0. In general, this symbol means it's a screw axis of second joint and its coordinate in inertial frame. But this guy will depend on theta 1. Since now we fix theta 1 0, so we can find special values, numerical values for it. Let's call that S2 bar, as defined as S2 0 when theta y is 0. Okay, this guy is fixed at 0. So let's say, let's compute this. I hope we can compute it. S2, this bar, it has two components. Let's call that omega 2, 0, and the V of 2 in 0. So omega 2 in 0 is, for them, what is omega 2 in 0? Let's define omega rotate about screw axis. It's this direction is positive, right? So what is the omega 2 in 0?
Is
At frame.
0, 0, 1, 0, 0 omega.
0, 0, 1, okay?
1.
Screw axis. I didn't say this head is still unit, okay? Because there are too many bar or head things. I don't want to overload the notation. Let's assume that it's unit speed, okay, for now. Okay, and so since this case, we know pitch equal to 0, right? It's only a rotation. Then we know, based on the formula we had before, this guy equal to negative Q of 2 cross, sorry, is that omega 2 is omega 2 in 0 cross Q2 in 0. And the Q2 is arbitrary point on this screw axis. We can pick any point on the screw axis. It will all be the same, so I pick this one. Okay, this is the one here. And which I have, this guy is this negative, this is 0, 0, negative 1, because there's negative here, cross, what's the coordinate of Q2 in 0?
L1, 0, 0.
Yes, so that's L1, 0, 0. So you have a Z cross X, you have a Y, right? So that will be 0, negative L1, 0. So overall, I will have S2 bar 0 equal to 0, 0, 1, 0, negative L1, 0. That's my screw axis in the inertial frame, 0 when theta 1 is 0. Okay? So what I mean here now is, hold on. So in this case, let me summarize the result. In this case, TBS 0 theta 2. Okay, in this special case, we know this guy is independent of theta 1, so I know that it's the numerical value is S2 0 bar theta 2 times TB at 0, 0 with its M. Okay, any questions? Will this make sense so far?
Yes, makes sense.
Okay, good. All right. Now let's do, we do things one by one, right? So we first rotate the second about second axis. Now we rotate about the first axis. So similarly, so I wouldn't. So now I fix theta 2 now. Theta 2 doesn't change anymore. Let's assume that the current configuration is theta 2 equal to theta 2. Okay, so the second joint variable is equal to theta 2. Then I now the whole thing rotate together as a single rigid body. Okay, so rotate about the S1 axis. So what do you think the so let's fix joint 2 at theta 2. Then I rotate the whole link 1 plus link 2 together as a whole unit rigid body by theta 1 degree. And in this case, we will have, again, this is a rigid body operation, right? Motion characterized by T hat again. Let's call that T hat. Let me think. 1 is exponential coordinate S1 theta 1 times, before you rotate, is TBS theta, this part is 0, and this part is theta 2. Okay. We know this S1 is independent. In this case, independent of any joint. Okay. No matter what joint variable is, S1 in 0 in the O frame is always this axis. Okay. The joint motion doesn't move this screw axis. So let's say this guy is independent of theta 1 and theta 2. So but we can still somehow use the same notation as 1 bar. It's the same as it's just this numerical value, assume that. So in this case, S1 bar is omega 1, 0, V1, 0. Okay. And omega 1, 0 is, what is it?
It's 0, 0, 1.
Okay, 0, 0, 1. What about V1, 0?
0, 0, 0.
So it's negative omega 1, 0 cross Q1, 0. Q1, 0 is any point on the screw axis. In this case, I can choose the origin of the O frame, so it's entirely 0. Yes, you're right. So the whole thing becomes 0, 0, 1, 0, 0, 0. That's my screw axis 1 in the inertial frame 0. Okay, overall, so this is my I think this is correct, right? So this rigid body motion leads us to that TB is S theta 1 and theta 2 equal to this rotating operator or screw motion operator applied to the pose of the B frame before you do the operation. Okay, so if you plug in the previous step, you get TBS theta 1 and theta 2 equal to exponential of S1 0 bar, because I keep use the same notation, right? Theta 1 times S2 0 theta 2 times M. Any questions? Okay, and you can see this is kind of a product of matrix exponential, right? So it's called product of exponential formula for forward kinematics. Did we solve our problem? Initially, we select a frame, right? And we are trying to compute the frame pose as a function of theta 1, theta 2, and we derive this function analytically for this special case. All right. Any questions? If no question, let's think about, let's move to the general discussion. So far we use a very special case to derive the product of exponential. Let's now discuss the general case. I think that's become simple. Here is all the notations. I don't want to explain all of them. So regarding some notation, let's say typically, let's go back to this one again. Sorry. Let's make some remark to motivate the discussion of general notation. Screw axis is when I write like S2, it's coordinate free. I didn't say which coordinate system I want to use to represent this screw axis. Okay, I can represent it in O frame. I can also represent it in B frame or other frame. Okay, and typically we will attach a body frame, attach a frame to its link. Let's say suppose let me use another color. Suppose this is my body link. This is a Z of 2 hat. This is X of 2 hat. This is a Y2 hat. And this is attached to the link 2. So whenever you rotate link 2, this frame will rotate with you. Okay. And in this case, I'm going to ask you guys. So we say S2 in O frame is a function of theta 1. Now, what about, let's say, remark? What about S2 in 2? So then, does this depend on S1, theta 1 or theta 2 or both?
It just depends on theta 2. Oh, theta 1.
Theta 1?
Theta 1.
I think neither, maybe.
Neither. Okay, it's a constant, independent of theta. Okay, no matter what theta 1, theta 2 you choose, and this screw axis S2 does not change, right? And so it's independent of theta. So in general, we typically attach, right? We attach a frame I to link I at joint I, right? Just like what we did before. And attach a B frame, that's our frame of interest for computing the forward kinematics. And this SI in I is screw axis. It's almost like a local coordinate of SI. Think about SI as a coordinate-free screw axis, okay? You can represent it in different frames, and in some frames, it's constant. In other frames, it depends on other kind of configuration variables or joint variables. And this guy, SI in 0, this guy is a function of theta, right? This guy is a function of theta. This is SI 0. It's typically the function of theta 1 up to theta I minus 1. Typically, I will just write theta I. Okay. Yes, here I wrote this out explicitly. Okay. And there's a special vector, as we defined before, is that we can numerically compute this number, which we call as I bar. It's when all the theta are 0, we have a fixed reference configuration or joint position, all of them are 0. And then we can compute the numerical values of the coordinate for each screw axis. Okay, all with respect to the inertial frame or 0 frame. Okay, that's bar. And given those notations, again, our computation or derivation includes the following steps. The step 1 is still try to compute the configuration at home position, or all the theta 1 equal to theta n equal to 0. Okay, so typically you can recognize this home position configuration or pose very easily. You can write it down, and then you can derive the overall forward kinematics function by moving backward from the last joint. Okay, so for example, initially you are at M, and that's your initial. Okay, that's home position, home. Okay, now you fix all the other joints to be 0. You apply the screw motion across these about this this is Sn, right? You about this Sn coordinate, and then you will have this one. It's this rigid body operator that moves this frame or rotates this frame about Sn coordinate screw axis by theta n degree. Okay. So why, I may ask Liuben, why Sn at this time equals to Sn bar 0 based on our notation?
Because the theta 1 and the theta n minus 1 equals to 0, that means the SE3 is the identity.
Okay, yeah. In this case, you're right. Yes. In this case, here, all these guys are 0, right? And then so that by definition, this guy's by definition is that. Okay. So Sn does not only depends on, actually this guy only depends on I minus 1. So it's just the numerical value we computed when everything is at home position. Okay. Now after here, this is step 1, this is step 2, right? Step 2. Let's call that step 0. Sorry. Step 0 is configuration in home position, and this step 1, you apply the screw motion to the last joint, the nth joint. Now you're here now, okay? That's home. This is step 1. After step 1, you're here. Now you are trying to do this guy, okay? Move about this axis. The key is that rotating about Sn screw axis does not move the Sn minus 1 coordinate screw axis, right? Apply screw motion, this screw motion. Let's say this guy, this operator does not move Sn minus 1, Sn minus 2, so on and so forth. You apply only the screw motion to theta n, and only the things after theta n will move, okay? Only after the links after theta n will move. And all the bodies or links before that joint will not change. Okay, so this guy is still at the home position. Okay, so it's still Sn minus 1 bar when everything is 0, you compute it, and you can apply this to that again. So after n screw motions, overall forward kinematics formula is this formula. Okay. This is the POE, product of exponential for forward kinematics. Okay, let's summarize. Initially, you select a home position. You call that position all the joint variable to be 0. Okay, maybe like this, my arm. Then you rotate from the last joint. Apply screw motion from last joint. You rotate the last, my wrist here. Okay, and my elbow next. The key is that when you rotate your wrist, and it doesn't change my screw axis of my elbow, right? So I can still, so the same screw axis is still the same. It's still when the coordinate remains the same. It's still n-1 bar. Okay, and you keep applying backward, will not affect anything. So we will have a numerical formula like the forward kinematic formula like this. Okay, I hope that's clear. Now the question, at least I'm not sure for you, but for me is that maybe I ask Fujun, do you think we can apply screw motion from not backward, just from the first joint?
I think it can be.
Can be done, right? It should give me the same result, right?
Yes.
So the derivation here is based on a kind of a trick or convenient way that we apply this motion or screw motion that the screw axis we computed before didn't change. Then we can keep using the same kind of ice bar to do this screw motion and obtain the final result. Okay, now let's consider the case, a weird case. Okay, I'm not sure whether it bothers you, but at least bothers me. I have to figure that out. So what happens if the order is arbitrary or reversed? Eventually, I still have the same. I can, for example, in this case, I can apply screw motion first to theta n-1, then to theta n, then to theta 1, right? I can randomly pick the order, but eventually my pose, final pose will be the same. Okay, and to understand what happens if we apply the screw motion in a different order, let's consider the simplest case. Okay, just show you this is essentially the same. Let's say this is the top down view of the previous example of the simple example with one. Hold on. This guy, remember this guy. It's a 2R, 3 links, two kind of joints. If we look at this robot from the top, it's on the, these two arms are on the plane, same plane. So we will have something like this. L1, this is L2, this is our, suppose there's a gripper here, okay? This is my, hold on, yes. So screw axis will be a dot, it's pointing outside of my paper, okay? So that's screw axis 0 bar, this screw axis 1, 0 bar initially. Let's say everything is theta is this is I equal to 2, this is I equal to 1, okay? And now let's not do the backward one, let's do the forward one. So let's say, suppose I apply the screw motion or rotate about first axis first. Okay. So then I will have this, and that's the new configuration, right? So this will be my theta 1. Now, what I can see that this screw axis now, this screw axis now in 0, is this the same as S20 bar?
No, I think no.
It actually depends on S20. If I write it down more carefully, it depends on theta 1 now, right? Depending on how fast, how much I rotate the first joint, my axis is actually in the space that my axis is located at different position, okay? So the axis got changed, all right? And then I can apply another rotation, which is, let's call that, this is screw axis here, then I rotate again, this is my this. So this is my theta 1, this is my theta 2. So let's do this order to see what will happen, okay? So first of all, the first one, let's say after the first step, This is the first rotation. My screw axis, as I mentioned before, changes. So now I want to know initially my screw axis. Let's see. Let's say oh, I have written down here. So now I assume everyone is fine with this guy. Okay. That means the TB in S, somehow I use SB here, okay? What that means, T of B in the inertial frame or fixed frame, after you rotate about the first axis by theta 1, and you keep the second joint still at 0, that means you apply a screw motion. That's fine, right? Screw motion is S1 bar 0, theta 1 times M. I think this is fine, okay? Now, the theta, this screw axis changes, right? So if I want to write down what this B of S theta 1, theta 2 is, what I can write down is like following, okay? So then is this correct? And I'm going to write down. Let's write it down like this. This is TBS theta 1, 0, okay? So after you rotate about the first joint by theta 1, that's your configuration. Now you rotate here by theta 2, then you apply screw motion again. Is this correct?
Yes, I think it's correct.
Yes, it's correct. Okay, it is right. It's just it's just here, this guy is does not equal to S20 bar. We need to compute it because this guy got changed after applying the first screw motion. Okay, and how it was changed. So S2 bar 0 got changed to S20 theta 1 after a rigid body operation, which is T equal to S1 bar 0 theta 1, right? So this guy equal to, as we reviewed, as we introduced before, you apply a screw motion, then the screw axis will change it, and that change is characterized by the adjoint of that operator, right? So that's S20 bar. In this case, you know that screw axis, this is 6x1 vector. This guy is 6x1. This adjoint is also 6x6. It's a 6x6 matrix, right? I think last time I even gave MATLAB example about how to apply a rigid body motion or operator to a screw axis. Okay, essentially here, and where this guy, where T is nothing but our first rigid body operation. Okay, that's the new result. Okay, we have a formula for this now. Okay. Now let's recall a fact. Not recall, let me tell you a fact. First recall, let's recall one. Recall a property that if a rotation matrix, you have a skew symmetric. This is a skew symmetric matrix from this vector equal to, if R is a rotation matrix, then this is equal to R skew symmetric omega R inverse or transpose. Remember this? Okay, and similarly, we can prove, maybe we didn't. So if, let's say, S prime equal to adjoint of T of S, okay, then we can say that the matrix representation of this twist equals to T times the matrix representation of S times T inverse. Okay. Do you remember what this is? I suppose S is, let's say S is omega V. What is this guy? Ruben, what is this? The matrix representation of a twist or screw axis.
It is yeah.
Is this right?
Yeah.
Okay, that's in little SE3. Okay. Hope you can connect all of this. Okay, so so this is 4x4 matrix. This is a 4x4. This is all 4x4 matrix, and these two equality, these two 4x4 matrix on the left and on the right are the same, equal to each other. Okay, that's a result. Let's recall that. Not recall. This is a fact. Okay, let me give you a fact. Let's accept this fact. Suppose you can prove it. Then, based on this fact, we can write this down. Okay, e to the S20 theta 2 is equal to e, because this guy is what? Is this, right? So we will say this is adjoint. Let's call that, this is adjoint T of S2 of 0 bar. That gave me another screw axis. Then I take the matrix representation and times theta 2. Okay, and by this fact, I know this relation, so this is equal to T times S0 T bar, S2 0 bar, T inverse times theta 2. Okay, theta 2 is a scalar. So overall, we will have T times E S2 0 bar and T inverse this theta 2 here. Okay. So the list step is okay to you or not?
It's okay to me.
This is due to the property of a matrix exponential, right? We have somehow seen we've seen this for several times already. Okay, so by this equation, then we can say, we can just say this one is correct, right? Then we just plug in our result. Then we got TBS theta 1 theta 2 equal to this guy times the other one. So will be, I directly plug in this equation. That will be this theta 2 bar, theta 2, sorry, S2 0 and times theta 2 T inverse. What we got is T, this guy, times T inverse, and whole thing times TSB theta 1 0, which is this one. Okay, let's copy that down. It's E to the S1 0 bar theta 1 times M. Okay, if you take a further look at this T is what? T is exactly this E to the S1 0 bar theta 1. And these two things got canceled out. Okay, so overall, you still have, because T is the theta 1, S1 0 bar theta 1, that's T, and times S2 0 bar theta 2, and this canceled. This is M. All right, we still have the same, although we start from a different order, we still obtain the same result. Okay, any questions? Okay, now we're done with the product of exponential for so for robotic kinematics, forward kinematics. Okay, it's very simple. In order to compute this formula, all you need is to find screw axis at home position. So that means S1, S2, Sn bar, okay, when all the joints are 0. Okay, and then the formula can be written down immediately. I wouldn't go over this example again, so this I would say become your homework. Okay, I think we spend a lot of time explaining every single steps. I think we should be good to go.